Today we are going to look at factorization of polynomials. Suppose D is an integral domain. A polynomial f of x from d of x, which is neither the zero polynomial nor a unit in d of x, is said to be irreducible below D if, whenever f of x can be expressed as the product of two polynomials g of x and h of x, where g of x and h of x belong to d of x, then either g of x or h of x is a unit in d of x. A non-zero non-unit element of d of x which is not irreducible over D is said to be reducible over D. Now let's look at a few examples. Now look at the polynomial f of x equal to 2x squared plus 4, which I can write as 2 into x squared plus 2. Now I know that 2 is a unit over the set of rational numbers, but it's not a unit over the set of integers, while x squared plus 2 is not a unit over either q or z. Hence, 2x squared plus 4 is irreducible over q, but it is reducible over z. Similarly, the same polynomial 2x squared plus 4 is irreducible over R, but reducible over C. Since in C I can factorize it in terms of two polynomials of degree 1. Similarly, the polynomial x squared minus 2 is irreducible over q but reducible over R. Now if I look at the polynomial x squared plus 1, it is irreducible over z3, but it is reducible over z5 because I can write x squared plus 1 as x plus 2 into x plus 3 in z5 of x. Now we look at a reducibility test for polynomials of degree 2 and 3. Suppose f is a field. Then a polynomial f of x over f with degree 2 or 3 is reducible over f if and only if it has a 0 in f. Let me prove that. Suppose f of x can be written as a product of two other polynomials g of x and h of x, both of which have degree less than f of x. Since I know that degree f of x is equal to degree of g of x plus degree of h of x, and I also know that the degree of f of x is either 2 or 3. Hence at least one of these two polynomials g of x and h of x has degree 1. So let me assume that the polynomial which has degree 1 is g of x and let it be equal to x plus b. Then I know that minus a power minus 1b is a 0 of g of x and therefore it's a 0 of f of x also. Now let me go to the converse of that. Suppose I know that f of a is 0, where a is an element in f. Then by the factor theorem, we know that x minus a is a factor of f of x and therefore f of x is reducible over f. Next, we define primitive polynomials. The content of a non-zero polynomial a(n) x raised to n plus a(n minus 1 x raised to n minus 1 and so on up to a0, where the a's are all integers, is the greatest common divisor of the integers a(n), a(n minus 1 up to a0. A primitive polynomial is an element of z of x with content 1. In other words, a primitive polynomial is a polynomial such that the GCD of all the coefficients is 1. Next we go to Gauss's lemma. The product of two primitive polynomials is primitive. Let me prove that. Suppose f of x and g of x are primitive polynomials, and suppose that h of x, which is a product of f of x and g of x, is not primitive. If it is not primitive, then I can find a non-zero GCD which is not equal to 1 for the content of f of x and g of x. So let P be a prime divisor of this content, and let f dash of x, g dash of x and h dash of x be the polynomials obtained from f of x, g of x and h of x by reducing the coefficients modulo p. Then f dash of x and g dash of x belong to the integral domain Zp of x, and f dash of x, g dash of x into g dash of x is equal to h dash of x, which is equal to 0, the 0 element of Zp of x. Why? Because p is a common divisor of all the coefficients of f(x) into g of x. Therefore, I know now that f dash of x and g dash of x belong to Zp of x, and Zp of x is an integral domain. Therefore, f dash of x is equal to 0 or g dash of x is equal to 0. This means that either p divides every coefficient of f of x or p divides every coefficient of g of x. Hence, either f of x is not primitive or g of x is not primitive. This is a contradiction, and hence our proof is complete. Now let's go to the next result. The next result says that reducibility over Q implies reducibility over Z. That is, if a polynomial is reducible over the set of rational numbers, it is also reducible over the set of integers. So let f of x be a polynomial over the set of integers. Now if that particular polynomial f of x is reducible over Q, then it is reducible over Z. Let me prove that. Suppose f of x is equal to g of x into h of x, where g of x and h of x are elements in Q of x. We can assume that f of x is primitive, because if it is not primitive, obviously we can divide both f of x and g of x by the content of f of x. Let a be the least common multiple of the denominators of the coefficients of g of x, and let b be the least common multiple of the denominators of h of x. Then a into b into f of x is equal to a into g of x into b into h of x, where a into g of x and b into h of x are polynomials over z. Let C1 be the content of a into g of x, C2 be the content of b into h of x. Then a into g of x is equal to C1 g1 of x, and b into h of x is equal to C2 h1 of x, where both g1 of x and h1 of x are primitive, and ab into f of x is equal to C1 C2 g1 of x h1 of x. Since f of x is primitive, the content of ab into f of x is ab. Also, we know that the product of two primitive polynomials is primitive, and hence the content of c1 c2 g1 of x h1 of x is c1 c2. Therefore, ab is equal to c1 c2 and f of x is equal to g1 of x into h1 of x, where g1 of x and h1 of x are polynomials over z, over the set of integers, and degree of g1 of x is equal to degree of g of x, degree of h1 of x is equal to degree of h of x. Next we come to the mod p irreducibility test. Suppose p is a prime, and suppose that f of x is a polynomial over z with degree f of x greater than or equal to 1. And let f1 of x be the polynomial in Zp of x obtained from f of x by reducing all the coefficients of f of x modulo p. If f1 of x is irreducible over Zp and degree of f1 of x is equal to degree of f of x, then f of x is irreducible over Q. Now we are going to prove this theorem. From the proof of the previous theorem, we know that if f of x is reducible over Q, then f of x is equal to g of x into h of x, with g of x, h of x polynomials over z, and both g of x and h of x have degree less than that of f of x. Suppose f1 of x, g1 of x and h1 of x are the polynomials obtained from f, g and h by reducing all the coefficients modulo p. Now I know that degree of f of x is equal to degree of f1 of x. And so we have degree of g1 of x is less than or equal to degree of g of x, which is definitely less than degree of f1 of x. Again, degree of h1 of x is less than or equal to degree of h of x, and again that is less than degree of f1 of x. But I know that f1 of x is equal to g1 of x into h1 of x, and this contradicts our assumption that f1 of x is irreducible over zp. The converse of the above theorem need not necessarily be true. If f of x belongs to zx and is reducible over zp for some p, f of x may still be irreducible over q. For example, look at this polynomial 21x cubed minus 3x squared plus 2x squared plus 8. Then over z2, f1 of x is x cubed plus x squared is equal to x squared into x plus 1. But over z5, f1 of x has no zeros and therefore it is irreducible over z5. Hence, f of x is irreducible over q. Next we come to what is called the Eisenstein's criterion. Suppose f of x is equal to an x raised to n plus an minus 1 x raised to n minus 1 and so on up to a naught is a polynomial over the set of integers. If there is a prime p which does not divide an but it divides all the other coefficients an minus 1, an minus 2 and so on up to a naught, but p square does not divide a naught, then f of x is irreducible over q. If f of x, let me prove that. If f of x is reducible over q, I can find elements g of x and h of x in over the set of integers such that f of x can be written as a product of g of x and h of x. And the degree of g of x and h of x lie between 1 and n. Now let those two polynomials g of x be br x bar r and so on up to b naught, and h of x is cs x bar s and so on up to c naught. Since p divides a naught, p square does not divide a naught, and I know that a naught is equal to b naught into c naught. It follows that p divides exactly one of b naught and c naught. Hence, suppose p divides b naught and p does not divide c naught. Since p does not divide an, which is equal to br into cs, we know that p does not divide br. So there is a least integer t such that p does not divide bt. Consider at which is equal to bt into c naught plus bt minus 1 c1 and so on up to b naught into ct. Clearly, p divides at, and by the choice of t, every term on the right after the first one is divisible by p. Hence, p divides bt into c naught as well. But p is prime and p does not divide bt. P also does not divide c naught, and hence we have a contradiction.